back to 3120. We are carving our way through chapter 26, and we have finished chapter 15, or lecture 15, lecture 16. Today we're going to start intramolecular Aldol reactions. So this will be lecture 17. All right, so as the name implies, we're going to be looking at aldol reactions that happen within the molecule itself, and it's going to be up to us to predict what the product will be, and it'll also be up to us in order to determine how to control whichever product we want to make. So let's take a look at an example. All right, so if we take this compound and if we treat this with potassium hydroxide, so you have your hydroxide base, my question to you is what are the potential, what is a potential product? What are you going to be looking for when you treat this with base? You want to look for acidic protons, alpha protons. So let's first identify those. You have alpha protons here, you have another set here, and then here you have another set. So maybe we can label these A, we can label these B, and we can label those C. So the other thing that you need to look at is you got to think about if we deprotonate and form an enolate, and it's going to form intramolecularly, where or how is that going to happen? So if you remove HA, you can imagine enolate, and then this would come and react here. That's one potential scenario. Another potential scenario is if you form the enolate here, and then this carbanion reacts right there. Another potential scenario is if you take HC, form an enolate over here, and then have that react there. So we have three different scenarios, but which one is it going to be? So if we start with the first one, you can see here that, yes, it's likely to remove those protons, but if you did this, you would generate a 1, 2, 3-membered ring, which is really quite unfavorable in organic chemistry. Similarly with HB, 1, 2, 3-membered ring. So these two are not viable options. In contrast, if we remove this proton, 1, 2, 3, 4, you generate a 5-membered ring. So let's take a look at what that will look like. So let's first form the enolate, as I'm showing you here. And what we're going to do is you're going to now have this enolate come and attack through an intramolecular type of reaction. And what you're going to end up generating is that 5-membered ring, as we promised, and a molecular scaffold that's going to look like this. This will pick up a proton from the conjugate acid of hydroxide. And this will be one of your non-hydrated or non-dehydrated aldol products. If you do dehydrate it under the basic conditions, you will go through that E1CB mechanism that we talked about way back at lecture 13. You form that enolate, electrons will come back down, and you kick off hydroxide group. So in terms of the reaction, this would be your major product. Now you might be thinking, okay, that's great, but how does the hydroxide know that this is the best place to enolize? Well, it really doesn't, and it's actually going to take all three different acidic protons at different times. But once it removes, let's say, HA and tries to react here, there's just too much energy to make that three-membered ring. So what it's going to do is the enolate is going to simply go back and pick up a proton and go back to the starting material. It's only until it takes these protons when a productive, favorable five-membered ring forms. All right, so just remember, 5 and 6, 5 or 6-membered rings are favorable in organic chemistry. 3 to 4-membered rings and like 8 to 13-membered rings are not so favorable. If you did treat this compound, however, with LDA, what would you actually get? And LDA, remember, is a sterically hindered base. It's not reversible like potassium hydroxide. So once it removes either of those protons, it's irreversible. So it's not going to go back, and what you will end up actually generating are a mixture of products. You'll end up generating a collection of 3-membered rings and 5-membered rings. So really, it depends on the base and the conditions that you have, in addition to what your starting material looks like. All right, so let's look through some other examples. I just want to make sure I have the right number of carbons. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Okay, good. So if we treat this compound with sodium hydroxide or potassium hydroxide, let's ask the same question. What are the major products, or what's going to happen? So apply that same strategy. Look for potential acidic protons, and here, just like in the other molecule, we had 3 different sets of acidic protons, and then go through the different combinations. Okay, so if we look at HA, you can see that you generate a 1, 2, 3, 4, 5-membered ring. Okay, not bad. We know that's favorable. If we look at HB, we form a 1, 2, 3, 4, 5-membered ring as well. Interesting. And if we look at HC, we'll form a 1, 2, 3, 4, 5, 6, 7-membered ring. Okay, so we have 7, 5, and 5. So under these thermodynamic conditions, we know the 7-membered ring is not the most favorable. 5-membered rings are much better. So we can scratch out this one for now, but let's take a closer look at what those 5-membered rings will look like. So let's take a look at, it doesn't really matter which one we look at first, but maybe let's look at scenario A with protons A. So if we remove these protons, we'll generate this compound here, and then this will come and react here to form your 5-membered ring. So if that happens, So what you'll end up getting is this species here after a proton transfer. Just adding that proton transfer because, yeah, I'm kind of running out of space here. But you can see that's the key carbon-carbon bond that's formed. And then now let's take a look at the other scenario. So scenario where we take the HB protons. Okay, so your base will come, remove those protons. And then this will come down. This will come and react here to generate that species. And then what you're going to end up having is a compound that's going to look after proton transfer. Molecule that looks like this. So we have two different 5-membered rings. And it's hard to understand or distinguish what their stabilities are relative to one another. So let's continue, and we're going to heat these up and dehydrate them. What is it going to look like? So if you dehydrate using the E1CB mechanism, you'll form a double bond here. That's your product. Let's call this B. If you do the same thing over here and you form a double bond here and dehydrate, you will generate this compound here, which we'll call compound A. So question is, which one is, you know, they both look like nice solid structures, 5-membered rings, but which compound is going to be the major compound, major product? Think about that for a second. Well, let me ask you this. Which compound is more stable? They're both double bonds. Which one is more substituted? This double bond here has 1, 2, 3 things attached. Let's not count the hydrogen. This one here has 1, 2, 3, 4 things attached. Remember Zaitsev's rule. Zaitsev's rule from second-year organic chemistry tells you that the more branched, the more substituted double bonds are, the more stable they are. So in this case, product A is our major product. But it was hard for us to determine that until we actually dehydrated it. Whereas this compound here is your minor product. Now lastly, we didn't concern ourselves with the 7-membered ring, right? But if we did want to make that 7-membered ring product, how would we do that? If we want to look at HC, imagine a scenario like that. A good base to use would be LDA because it's sterically hindered. It's going to take the least sterically confined proton. So it's going to take these ones, which are much easier to enolize, and then you'll get that irreversible reaction happening over there. So let's draw what that 7-membered ring will look like. 1, 2, 3, 4, 5, 6, 7. 7-membered rings are a bit tricky to draw, especially if you've been drawing 6-membered rings for a while, but that's a 7-membered ring. It's definitely not the favorite product from a thermodynamic standpoint, but if you heat it up, this will be your compound. 1, 2, 3, 4, 5, 6, 7. Okay? This is the kinetic product. Whereas both A and B are thermodynamic products. All right, and then the last thing I just want to talk about with respect to intramolecular aldol reactions is this here. If we take this compound, treat this with potassium hydroxide, we actually have two different scenarios as well. You could imagine removing these protons, forming a 1, 2, 3, 4, 5, 6-membered ring here, or you could imagine this scenario where we form a 1, 2, 3, 4, 5, 6-membered ring. So let's call this pathway A, pathway B. Both 6-membered rings, which one is it going to be? Let's take a look at pathway B for a second. If pathway B happens, this is what it's going to look like. Okay, so what you'll end up generating is 1, 2, 3. You'll generate your 6-membered ring. Okay, so 1, 2, 3, 4, 5, 6. So you can follow the carbons. But this ring here is a highly strained bridge complex. It really doesn't flex well because we already have a 6-membered ring there. So based on the geometry and its structure, this bridge strain complex is actually fairly unstable. So however, this is scenario A. If you look at scenario B, this is scenario B, and if you look at scenario A, and we form this structure like this, you can see that you're going to have two 6-membered rings that are, fused together in a nice in a nice structure that's devoid or free from any steric clash or strain complexes. And what that will look like when it dehydrates this one here. So this will be your major product. So this is just highlighting that, yes, I've told you 5 and 6-membered rings are good, but you have to take into account what that 5 or 6-membered ring will look like from a geometric point of view. And look out for strain complexes that might distort the structure. And if that's the case, then you always find the lowest energy compound when you're competing with 5 and 6-membered rings. Okay, so that concludes our lecture on intramolecular aldol reactions. Next up are enones. See you soon.